G'day everyone and welcome back to Simo's YouTube channel, really. This is now 2021. You'll notice that a few things are different here. Yes, that's correct. I am wearing glasses. That is correct. I am losing a bit of eyesight and I might well have grown a little bit of hair, but don't worry about that. It's the same fellow underneath here. Okay, so what are we doing? Well, today we're doing complex plane, or we're actually graphing things on the complex plane. So hopefully at this point you're familiar with complex numbers, the idea of z being a complex number. Z can be written as a plus bi, the real and imaginary component, or x plus yi, whichever you prefer, it doesn't really matter. But what about if we want to graph things on our complex plane or our Argand plane? Okay, we've got the Cartesian plane, which would be x and y. In the Argand plane we've got real and imaginary. I've got a couple here and I want to work through these ones to give you the idea of the process around it. Just look at this one in the black texture at the moment. Let's talk about what that is telling me. This is saying the set of points. Curly brackets is saying the set of points, or the things that fit this of z. Well, we interpret z to be a complex number. That's a kind of a given. You see z, assume it's a complex number unless it says otherwise. So it's the set of points of complex number z such that, two dots, such that, this is like a constraint that you're giving it, that the absolute value or the modulus of z, or the distance or the length of z is equal to 3. So that whole thing is telling me, show me the points where the modulus is equal to 3. Well, modulus is kind of like radius, isn't it? So if I want the modulus, the absolute value of z, to be 3, on here what I'm going to find is that that point there is going to fit that, because that would be 3 plus 0i. Find the modulus of that, you're going to get 3. You would also find this point here would work in the same way. You're going to find this point here in the same way, this point here in the same way, and if I kept going I would find a point here, and one here, and one here, and you will find that any of the points that form the circle of radius 3 will fit that. So if you see something in this format, the absolute value of a complex number, then you're looking at a circle. Now because this one is equals, then really what I should do, I should draw that line in as a solid line, because only those ones exactly on the circle will fit this one in black. But this one, if I did this less than or equal to, well then I would have to shade all that area, because the things on the inside are going to be less than or equal to 3. Similarly, if I made this greater than, then I'd be looking at outside, and if I got rid of that part there, then I'd have to dash that line around the outside, wouldn't I? Because that would mean that I'm not including the ones that equal 3, only those that are less than 3. So this is one of the key formats around graphing things on the complex plane. See this format, thinking circle, looking at the greater than, less than or equal to decide which area you're actually going to use. Second one. This one is kind of similar, but instead of looking at the modulus or the magnitude or the length, we're now looking at the argument or the angle. So this one is saying, I want anything that is between pi on 4 and 3 pi on 4. So pi on 4 is out this way. Let me get, here we go. Let's do this one in green. So pi on 4 is out that way. Now, it goes on forever, doesn't it? And then 3 pi on 4 is going to be out this way. So this one here is talking about the region that is between. Any complex number, this point here will have an argument between there. This here will have an argument. Of course, if I came here, that argument is going to be less than pi on 4 and therefore wouldn't fit this. So this one's about circles, this one's about kind of a range and angle. And of course, if we were to give a question where it said this, and then say the union with this, well then everything that is shaded would have to be included. And if it said that and the intersection between those two, then it would only be this section here that matches both of them. So all your set notation idea of union, complement, intersection, all of that, you can throw straight back in here because we're really just graphing spaces. Right, that's one way of doing things there, that's one style. The next style is a little more complex, but if you understand it from the get-go, it's no harder. These ones here, I want to just work for a moment with this here. Just work with that. Z minus 2i. So if I have Z minus 2i, it doesn't look like anything I can deal with, but I'm going to write it like this. I'm going to write it as Z minus 2i. Now remember, Z is any complex number. So this could be any place on the Argand plane, and I want to subtract away some other complex number. So really, aren't I looking at the difference between two complex numbers? I'm looking for the difference between two places in space. So Z could be, let's just pick a point, Z could be there. Okay? And 2i is going to be there, isn't it? So isn't this asking for me to tell you that there? The difference between two? And then when I take the magnitude of it, isn't that asking for a distance between 2 points on the Argand plane? So this sort of thing here is actually looking for the distance between 2 points on the Argand plane. This over here is doing exactly the same, just that the point that we're using is not on the imaginary axis. This would be Z minus plus 4. That would be there, because it's on the real axis. So that idea of the distance between, or the difference between, because it's magnitude, a random point and this point is really important when we start graphing this. Okay? Let's get rid of this. So, what I'm going to do, and this is not going to make sense initially, but it will in a moment, I'm going to graph this point and this point. Get rid of this. So that one there is the point 2i, right there, color-coded, 2i. Then this here, remembering that I want to set it up in this format, a number minus something. So this is plus 4. It looks like minus 4, but it's actually plus 4, because it's minus plus 4. Now let's read the whole equation. It says, give me the set of points of complex number Z such that this part of the equation equals this part of the equation. Well, both of these are distances, aren't they, because of modulus. So tell me, would, and excuse my drawing ability, but would, oh no, I can do it exactly, there we go. Would that point there in the black dot, would that point be exactly the same distance from here and from here? Yeah. It would, wouldn't it? Right? So that point there seems to fit that. Would this point here, again within construction my drawing, appear to be equally distant from those two? Yeah. And would this point here also be equally distant? And would this point here? Can you see how if I choose all these points, what am I forming? A line. Exactly. So this format is going to say there is a line of points that fall between these 2 points that will satisfy that equation. So any point on this line will be one of the complex numbers Z that fit that equation. Do you see how if you can break down this part here and understand what they're telling you, then it's actually a really easy question to see. But if you can't, then people look at this forever and they're like, I don't understand. This second one here, I put this here mainly because See how it's minus 2 minus 2i? Well, I would rewrite that as z minus 2 plus 2i. Because then it's clear, this is the point that I actually want to plot. That would be that point there. That would be the dot that I'm going to use. And here it would be z minus 1 plus 3i. Minus 1 plus 3i, I'd be there. So by setting it up in this format, the difference idea, then it's easy to see where the points are going to go. And then you just find that perpendicular bisector between the 2 points, and you're away. Anyway, I forgot you were there. Hopefully this has made sense to you. If it hasn't, I'll do a couple of examples later on, and hopefully I'll get them up as well. Thanks for watching.